Electrons in atoms occupy discrete energy levels, yet they do not remain excited indefinitely. When an electron drops to a lower state, it releases a photon, but this spontaneous emission occurs randomly in direction and phase. This lack of coordination prevents natural light sources from producing the intense, directed beams we associate with lasers. After that first surprise, we can slow down and trace the mechanism behind stimulated emission explained, the heart of lasers from the first physical step, so the effect stops feeling mysterious and starts feeling engineered. To understand how lasers function, we must first establish the quantum mechanical framework governing electron behavior within an atom. Unlike classical models, where electrons orbit freely at any distance, quantum mechanics dictates that electrons occupy discrete energy states or shells. These states are quantized, meaning only specific energy values are permitted for a given atomic system. Consider the hydrogen atom as our primary example, where the electron resides in its lowest possible configuration known as the ground state. In this stable condition, the electron possesses minimum potential energy and remains bound to the nucleus without radiating further energy. Any transition to a higher shell requires an exact input of energy matching the precise gap between these quantized levels. This strict requirement for discrete energy differences creates the necessary conditions for controlled photon emission later in our analysis. Without this foundational structure of fixed states, we could not achieve the coherent light production characteristic of laser technology. Pause 0.8 to understand how lasers function. We must first establish the baseline behaviors of electrons interacting with light energy. When an electron absorbs a photon, it gains exactly enough energy to jump from its ground state to a higher orbital level. This process requires precise matching between the incoming photon's frequency and the specific energy gap within the atom. In contrast, spontaneous emission occurs when an excited electron naturally decays back to a lower energy state without any external trigger. The timing of this decay is entirely random, meaning we cannot predict exactly when or in which direction the emitted photon will travel. Imagine a ball rolling down a hill versus being pushed up by a hand. Absorption requires that external push, while spontaneous emission happens on its own accord. This inherent randomness ensures that ordinary light sources like bulbs emit photons with varying phases and directions, rather than synchronized waves. Having established these random behaviors, we now examine how an external photon can force a synchronized release of energy. Pause 0.8 Stimulated emission is the fundamental process that allows lasers to generate coherent light through a precise atomic interaction. When an incoming photon encounters an atom already in an excited energy state, it does not get absorbed but instead triggers the release of stored energy. This interaction forces the excited electron to drop back to its lower energy level while emitting a second photon that is identical to the first one. The resulting photons share the exact same frequency, phase, and direction of travel as the original incident particle. For example, if you imagine two synchronized swimmers moving in perfect unison, stimulated emission ensures the new swimmer matches their rhythm exactly rather than creating a chaotic splash. This precise duplication is what distinguishes laser light from ordinary sources, where emitted photons move randomly with varying phases and directions. Understanding this mechanism sets the stage for recognizing why we must achieve population inversion before amplification can occur. Pause 0.8 In standard thermal equilibrium, atoms overwhelmingly occupy their lowest energy ground state rather than excited states. This distribution means that when light passes through a material, absorption events outnumber stimulated emission events by orders of magnitude. Consequently, the beam loses intensity as photons are absorbed rather than gaining strength through amplification. To achieve net light amplification, we must force more atoms into an excited state than remain in the ground state. This condition is known as population inversion and represents a critical statistical requirement for laser operation. Consider a hypothetical material where 100% of atoms occupy the upper energy level while 0% occupy the lower level. In this scenario, every photon interaction triggers stimulated emission rather than absorption, creating exponential growth in light intensity. Without achieving this inverted state through external pumping mechanisms, no amount of optical design can produce laser output. Having established that we must invert atomic populations, we now examine how mirrors create feedback loops to sustain this process. Pause 0.8 to sustain the chain reaction of stimulated emission. We must trap photons within the gain medium using an optical cavity. This structure consists of two mirrors positioned at either end of the laser rod, with one mirror being fully reflective and the other partially transparent. When a photon is emitted through stimulated emission, it travels toward these mirrors rather than escaping into the surrounding environment. The fully reflective mirror sends the photon back through the medium, where it encounters another excited atom to trigger additional emissions. This creates a feedback loop, where photons bounce repeatedly between the mirrors, exponentially increasing the number of coherent light particles. Think of this process like pushing a child on a swing at precisely the right moment to maintain and increase their motion over time. Without this resonant cavity, the stimulated emission would occur only once per photon before it dissipated into random directions. The partial mirror allows a small fraction of this amplified light to escape as our usable laser beam, while maintaining internal amplification. This geometric arrangement ensures that only photons traveling parallel to the axis remain trapped long enough to contribute significantly to the output. Pause 0.8 Stimulated emission is not merely a source of light, but an exacting copying process that enforces strict identity between the incoming photon and the newly emitted one. When an excited electron interacts with a passing photon, it releases a second photon that matches the original in frequency, direction, polarization, and crucially phase. This mechanism ensures that every subsequent emission event adds another wave perfectly synchronized with its predecessor rather than creating random interference patterns. Imagine two sine waves traveling through space, where one triggers the other to emerge as an identical twin moving in lockstep across time and amplitude. The result is a macroscopic beam of light composed of countless photons oscillating together as a single coherent entity instead of independent particles. This precise alignment forms the foundation for laser properties that distinguish them from ordinary thermal sources like incandescent bulbs or sunlight. This synchronized wave structure enables the next stage, where a portion of this coherent light escapes through a partially reflective mirror to form the usable laser beam. Pause 0.8 to transform internal amplification into a usable beam. The optical cavity must include an output coupler. This component is a mirror engineered with specific transmission properties that differ from the fully reflective end mirror. While one surface reflects nearly all photons back to sustain the chain reaction of stimulated emission, the opposite surface allows a precise percentage to pass through. Consider a standard high reflectivity mirror, which might transmit less than 0.1% versus an output coupler transmitting 5%. This controlled leakage prevents total internal reflection from trapping energy indefinitely within the gain medium. As photons bounce repeatedly between these surfaces, they build intensity until the partial transmission releases a steady stream of coherent light. The resulting beam remains collimated because only photons traveling parallel to the cavity axis survive multiple reflections without diverging. This selective extraction ensures that the output maintains the directional properties established during the amplification process. Understanding this balance between retention and release is essential before we examine how these beams interact with matter in practical applications. Pause 0.8 Stimulated emission requires an excited electron to encounter a photon, triggering the release of a second identical photon. This process demands more atoms in the upper energy state than the lower one and relies on mirrors to sustain the chain reaction.